Today, I'm gonna start about the vector space, which is very fundamental in mathematics and many field of the physics. I believe all students already know what is the vector space, but I'm gonna emphasize the importance of the vector space once more, and that is very important to understand the electron behavior in a solid. Okay, so let's start most easiest way is this example. If you have a vector in a three-dimensional spaces, this vector A can be described by each component, let's say A1, 2, 3, and the unit vector here I, J, K means the unit vector direction of X and Y and Z. And each X and Y and Z unit vector or I, J, K has orthogonality and normalization conditions. So any kind of a vector A in a three-dimensional space can be expressed by this linear combination of unit vector, right? So if we have each component, then you can easily uniquely determine the vector A. So that implies the vector, to describe the vector A, we need three scalar quantity. Let's say A1, A2, A3. And how about the four-dimensional space? Oh, okay. And one more thing is we need at least three unit vector, which one is called the basis vector. And how about if we extend not three dimension, if we play with the four dimension, yeah, we need one more unit vector and one more scalar quantity to determine the unique vector. And you can extend this idea to n-dimensional space, more general case. So if we define the next unit vector, let's say L, but it's not easy to describe in because we are living in a three dimension, right? But anyway, you can extend this dimensionality to number of n or to infinite. So you can guess we need a number of n scalar quantity need to describe the n-dimensional vector and n unit vector we need to describe the n-dimensional vector that is called the basis vector. Okay. So what is the meaning of this each element? To obtain the fourth element, what we have to do is taking the unique inner product to the vector A, then we gather this component. We know this inner product, or we call the scalar product, but the physical meaning of inner product is something more. For example, what is the meaning of the magnitude of A sub 4 in this case? This means, okay, so let's back to the three dimension. It's more easy to understand. This magnitude A1 is the component of the vector A, which one is parallel to the unit vector I, right? So if we have a 0 in A1, what you can say is there is no x component in this vector. Here, the x component physical meaning is just the direction, but we're going to extend the physical meaning of unit vector, more general case, for the general vector space. But please keep in mind, to obtain this scalar quantity, what we have to do is taking the inner product. And this value means the property of this unique direction of the vector A. Okay, we're going to generalize this idea. Okay, so one of the very powerful example is the Fourier series. We know any kind of periodic function can be expressed by the summation of sine and cosine. And I would like to rewrite this Fourier series in this simple form. Here, the C hat or S hat represent the kind of the orthonormal basis vector, and which one is actually sine cosine. If you define the inner product in this case by this integral, the general vector space inner product is defined by the integral. So we know the orthogonality of the sine cosine in a Fourier series, right? Okay. And to obtain each coefficient, what you have to do is taking the inner product. It's same. It's exact same meaning of this inner product things in three-dimensional vector or fourth-dimensional vector. Okay. And what is the meaning of magnitude of this coefficient in a Fourier series? This means the component of nth omega property in original function f. So let's say one of the example of the Fourier series is, you know, bitmap. When you're taking the, do you know the difference of bitmap file and the JPG file? Bitmap file is recorded the information. Let's for the simple way, let's think of the black and white image. Bitmap data represent some 0 to 255 corresponding. I don't know which one is black and white, but one is black, the other one is white. Maybe the other way. Anyway, this number represents the intensity of each pixel. And every pixel has this value. So this is kind of, okay, so more generally not the black and white, but we can say RGB. And each pixel has this number and three of these numbers corresponding RGB. So we can represent any kind of image. But to store the image, large image, it requires a lot of data space. So what we convert from bitmap to JPG is, you can, the amount of the size of the file is reduced when you convert it. But it looks like the same image, right? The idea is here. We can take the Fourier transform of the bitmap image and let's call it the high frequency term. The high frequency means very sharp term. And then take the reverse inverse Fourier transform. Then we got the image without high frequency term. What is the meaning of high frequency in this case? Image, if you have let's say, this kind of a square image, this is, let's say, black and white, and there's some abrupt change. And in a Fourier series, this one is combined by many kind of sine curve. You can make this kind of sharp image. And only the low frequency term means slow varying term. Let's say something like this, and something like this can be described many important feature of this sharp image. Okay, let's say, okay, this one is really good idea. To describe this square wave, even though we only have few terms, can get a similar image. But in order to describe correctly this square wave, we need infinite number, actually. Very large number we need. But even though we have only four number in case, what we need is four coefficient number. Then still we can obtain this some main feature of the image. So in a JPG, they lost the very sharp image part. But many photo, they don't need that kind of sharpness, right? So here what I'm saying is each component, each coefficient represent the amount of the characteristic of this original function at the given basis for the given basis vector. So we're gonna talking about the property of the electron. Sometimes we say this is the S electron, or the other one is the P electron or D electron. But sometimes we are saying this is the SD hybridization electrons, because they have both characteristic of the S band and the D band. S and D is kind of the basis vector in this case. Okay. So how we can obtain this coefficient is taking the inner product. Please remember that point. So from the bitmap to JPG, for example, if we take the photo of the some people, usually if we take the photo of the people, the image is usually symmetric, right? If we have a photo of the people, then this image has some kind of mirror symmetry. Not perfect mirror symmetry, but somehow the symmetry part is very large. So we taking the cosine Fourier transform instead of the sine Fourier transform, for the JPG. So JPG using the cosine Fourier transform because the symmetry of the most of the images, not all images, but it's generally they including many even terms. So if you extend the image of the bitmap and JPG by pixel, you can easily find the JPG is more smooth image compared to the bitmap. And that's why even though using the convert from the bitmap to JPG, I mean, even if you have a same image, same size of the bitmap, but the JPG will be different the file size because of the Fourier transform it depends on the details of the images. Okay? Anyway, so this is the one example of the vector space. And in a vector space, if we have a complete basis set, we can represent any kind of function in that vector space. That's a very important mathematical result. So once we know the wave function of the given problem from the complete basis set, then any kind of wave function can be represented by this basis vector. So this is the same, mathematically same, let's say, any kind of vector can be represented by the linear combination of the basis vector. Okay? So in many quantum mechanical mathematical representation, we know if this is the basis vector or the wave function of the given system, then any kind of wave function can be represented by this way. And also we are using the bracket notation for the wave function, and this means kind of integral, or in other words, this is kind of inner product. Okay? If you have any question about this kind of concept, please ask me. Okay, so let's back to the Fourier series again. I said Fourier series is the one very good example of the general vector space. And let me ask a question. Do you know who is this guy? Yeah, you're old guy. Now young guy said this is the Johnny. Okay, anyway. So this cartoon, the background of this cartoon means there's some kind of green characters is showing. What is the meaning of this one is this guy recognized his world is actually not the real world. It's kind of the virtual reality or the kind of can I say? Yeah, yeah. So after once he recognized, okay, this is not the real world, and when he take a look any kind of object, it looks like kind of the digital something. So why I show this cartoon here means if you really understand what is the meaning of the Fourier transform, then when you take a look this kind of rectangle, now it's kind of sum of the sine cosine. So everything is made by sine cosine. If you really understand the Fourier series, sometimes you can see this kind of situation. Yeah, it's kind of joke, but that kind of understanding is we need to real understanding of the nature. Okay. This is another joke. When I have some chance to talk with a foreign scientist, he asked me, how can you write down the Korean Hangul, especially for the vowels? So I said, okay, our vowel is consisted by three basis vector of this one. Let's call it Chun-Yeol, right? And fortunately, all my foreign friends are scientists and engineers. So they are very easily understand what I'm saying. Okay, so any kind of vowel we can make combine all these three basis vector. Fortunately, in this room, all students looks like understand what I'm saying. But when I give this joke to second grade or third grade undergrad student, only they partially understand what I'm saying. Okay, so let's say my last name is Yu. So only think about this vowel part. This is what I'm saying is this one. For this one, okay. So this is my notation, but you may understand what I'm saying. For the foreign student, can you understand?
Yeah, I use it.
Okay. Okay. So that's why we need only three basis vector to represent any kind of vowel, right? So if you understand this one, you understand what's the meaning of the vector space for the general case. Another easy example is MBTI. This I don't like this one, but now many young people like it. In very strange representation, in my understanding, because this is the actually for the MBTI they need only four basis vectors to represent the people's characteristics. It doesn't make sense. It's too simple, right? But anyway, in this representation, if we have a positive E, or they just mentioned about the negative E. This is the negative E, right? And this is negative S. So we need only, it means only four basis vectors. But sometimes they said this one is also E, and this one is, I mean, I think this result, but yeah, people said you are type of E, but some type of E is very, very strong E with very weak S. But some people has these characteristics, and people say this is S and this is E type. So to describe correctly people's personality, you need a certain amount of these characteristics, right? Okay, yeah, don't be serious, it's a joke. But I believe this 4 is too small basis number to describe the more correctly the personal the people's characteristics. Then we need much more basis vector, right? And we need something more. But anyway, so this is one of the example. Okay. Anyway, so I want to emphasize we are using such kind of vector base the vector space concept in our everyday life. Okay. Let's back to the quantum mechanics. The basis vector of the hydrogen atom, when you solve the Schrödinger equation, the solution forms kind of a spherical harmonics. And this spherical harmonics is purely mathematical quantity, right? It doesn't think about any quantum mechanics. It's, when you solve the the electromagnetic problem, you can also this special functions if you have a similar mathematical equations. But instead of this spherical harmonics, the linear combination of the spherical harmonics is more convenient. For example, this is the real shape of the spherical harmonics. And as you see here, if we say 0, 0, the square root 0, 0 is the spherical shape. And 1, 1 shows kind of donut shape, and this one shows kind of this, how can I say, anyway, I cannot say the name, but anyway, you can imagine. But instead of this one, the linear combination of these spherical harmonies, we can obtain the more familiar form of the orbital shape. Let's say the P shape, the P orbital or D orbital can be obtained by the linear combination of this one. Okay, so in most cases, X, Y, Z representation is easy to describe some vector in a vector space, three-dimensional vector space. But if you have a rotating lattice, then say this is capital X, capital Y, fusion is combined by the small x and y. And using this vector is more easier, right? But mathematically they are same, but you can choose the more convenient way to describe the situation. And also, if you describe in this linear combination instead of this spherical coordinate system, it gives us more information of the shape of the orbitals. Which one is more important and more easy to understand the interaction with the other atoms, especially in chemical problems. So, to describe this kind of p orbital, what we need is this related to these two corresponding y1 minus 1, y1 plus 1, and y1 0. And with some mathematics, to get py, we need 0, this one is 0, and this is maybe 1, 1. Or yeah, I over root 2 generate this p. Can easily obtain the description by the data group. Okay, so the p orbital is something like nothing else but the linear combination of this two spherical coordinate system. Yeah, it's not easy to understand why when we add up we obtain this one, but this figure is actually the square of the spherical harmonics, not this one. This guy, including the phase term, so it's not easy to describe in this three-dimensional image. But mathematically, when you add up these two guys, you can obtain this one. And maybe px can obtain, maybe taking the minus sign here. I'm not sure, but there is some kind of linear combination. And also pg need some linear combination of these three guys. Then somehow you can obtain the p orbital with this linear combination of the spherical harmonics. Okay. This is the name of the author of some book. I like this guy's book because they including many important concept to understand solid state physics. So if you have a chance, please take this book, this guy's book. Okay. Anyway, so that's why I'm saying the linear combination of the vector space is important in not only this simple orbits, but for the band concept, we also need such kind of a linear combination of the basis vector. Okay, so let's back to the next. Okay, from now on, I'm going to give a simple lecture, about the band theory. What I found is we already learned the band theory in a solid state physics when you was undergrad course. Most of the students, I believe, already learned it. But many students, they do not understand what's the meaning of the band when they read the paper. So I wanna give some information to the student. If you take a look some band structure in a research paper, what's the meaning of this band? Yeah, that's what I'm gonna talking to you. So I'm gonna starting from the hydrogen molecules and also 1D chain molecules, and can talk about the band structure in a 1D chain model, chain molecules, and let's move extend it to two-dimensional or three-dimensional band structure, and so on. Okay, but okay. So the goal of this lecture is to read and understand the band diagram. Okay, and I hope this will be fun, but it's not that difficult. If I'm asking you following all mathematics, maybe it is difficult, but still I'm asking you to catch the main idea of this lecture. Okay, band structure kind of the anatomy, genomes of electron structure of the given materials. So many researchers try to calculate the band structure of the given materials. And once they obtain the band structure, many theorists said, okay, we got everything. We can calculate everything from this band. But in many experimentalists, it's not easy to understand what's the meaning of this diagram. Okay? So our goal is how we can understand this kind of given band structure. So if you know the band structure material, they can calculate the electric or thermal conductivity and heat capacity, and also optical property, means they can calculate the reflective index or the color of this material, or the elastic characteristics, and also magnetic properties, and so on. So that's why people try to calculate the band structure. And let's start the hydrogen molecules. If we have two isolated hydrogen atoms, let's say this is 1, this is 2. And if they are separate long distance, there's no interaction, and their Hamiltonian, let's say H1 and H2, has a energy of each electrons. And let's say this is S state, so ES. And let's taking these two atoms close, and they start to interact. And they start to share the electrons. And we need new wave functions. Okay? And new energy of the electrons. This is the Hamiltonian of these molecules. This is for the atoms. This is now we are talking about the molecules. And this new wave function can be described by the linear combination of these two wave functions, because they form the complete set of the vector space. So new wave function must be linear combination of these two basis vectors. That's why I'm talking about the vector space before I'm talking to you. Okay, so what the remaining problem is finding this coefficient. Then you can obtain the psi, because we believe we already know everything of these separate atoms. Okay, so we already know the Hamiltonian for each atom as the S state energy. Okay, sorry, this is maybe single state energy, single atom energy. Anyway, so we know this one. This is what we know. And if we're taking the in this side, taking the inner product of the wave function 1 and 2, we obtain this result. Okay, this is just a rewriting of this one with this guy. And if you're taking the inner product, let's say this one, this part is C2 is just the scalar quantity, and we obtained here just a moment. Okay, so let's say we have a 4 component of this one. This one also. In something like this. And let's define new variable called E0 and beta, and it's corresponding to this guy and this guy. Let's say they are physically same because it's a inner product of, sorry. They should be same because two atoms are identical, right? And also, this is off-diagonal terms, so we can rewrite a multiplication in this form. Because the right-hand side, this guy is this one, and this one generates this form. You can do it by yourself. And our goal is finding the coefficient. Actually, we don't know this number, but let's assume we know this is some number. And what you have to do is solving these matrix equations and finding the coefficient is to find the non-trivial solution of this one. The determinant of this matrix must be 0. So the unknown energy E is expressed by E0, which one is corresponding on-site energy we call, and plus minus beta, which one is called the Hoping matrix value. Okay, so what is the meaning of on-site and Hoping? I'm gonna explain. But please remember that the E0 is combined of their own one first electron and the first electron, first atom and first atom, and the second one and second one. But this one is combined by one atom and the other atoms. So the physical meaning of the beta, the hoping is the electron is moving one side to the other side, the probability. So now the calculation of beta is something like this. This is the kinetic part of the hydrogen atoms, and this is two potentials for atom 1 and atom 2. And actually these guys, we can separate this guy, and this part is nothing else but this is the single atomic Hamiltonian, so we can write this form. And this guy is this is for the one electron, the electron 1 at the site 1, and this is electron at the site 2. So usually they can be disappeared. We got this one for the beta. So means the one electron is moving to one side to the other side. This is the meaning of the beta. And usually we are talking about the one. Now we are talking about the 1s electron. 1s electron, and the Coulomb attraction potential that itself is negative. So the beta value is usually negative. So please keep in mind beta is usually negative. So the energy of the combined system is E0 plus minus beta, and the corresponding wave function is linear combination of wave function 1 and 2. The sign is plus minus, and this number is we need to normalization. So we don't need to pay attention for this part. Anyway, so we have a sum or subtraction of two wave functions and form new wave function in a combined state. And this is nothing else but the bonding or anti-bonding orbital, which one you learn in a chemistry. So let's summarize. This is the first one is atomic orbitals and the other one. And we have a low energy here because B is corresponding E0 plus beta. The beta is negative, so they are smaller than E0. E0 means the some certain amount of energy. So we have a two state, which one is the low energy and the other one is high energy. And if you look the sign, this orbital is the in phase of these two 1s electrons. They form kind of a cloud, and this anti-bonding case, there is some node at the center of the two molecules. What's the meaning of this node? What's the meaning of this almost zero probability of the electron at the center? This cartoon tells us this shape is kind of electron, the density of the electron. So that means the electron can be exist in all this area. But in an antibonding case, the electron cannot be exist between them, because the two electron is a wave, so they form some destructive interference at the center. That's the meaning. Okay. So now what we learn is if you taking two hydrogen atoms, they made some bonding to lower the system energy by this making new wave functions, which one is making kind of constructive interference. So that's why this system is more stable compared to this separate system. That's why the hydrogen is existing as a molecular state is compared, not the atomic state in normal case. And if you give a high energy, we can separate the hydrogen atoms, okay? But somehow they are more stable. So that they generally form the H2. Yeah, I believe so far you already learned in chemistry, but let's extend this idea more general case. Okay, so let's back to this form of the wave function. This plus sign means two wave function is overlap and making some bondings, and they can make a constructive combination. But when you have a minus sign, they made some node at the center is kind of destructive construction combination in a wave function. Okay. So in anti-bonding case, the phase of each orbit is opposite, so they are cancelled out at the center. Okay, so let's extend this idea to the one-dimensional chain molecules. Let's number of n. And we assume we already know the J's atoms orbit. Let's say J here. This is the wave function, and we already know this one. And the total Hamiltonian of the system is Hamiltonian of each atom. The H1 means the isolated Hamiltonian of given molecules, given atoms. And this is the interaction terms. H1 means interaction between 1 and 2. and 1, 3 is interaction to 1 and 3. Right? And this is very important. Each state is orthogonal. So I state and J state, the linear combination, the inner product generate the delta function. And what we want to solve is total Hamiltonian, which one is given by this one. And we want to obtain the wave function and the energy. And because this new wave function must be linear combination of the given wave function, so we can write down this linear combination because they form the complete set of the this given problem systems. So new wave function must be destroyed by this linear combination. So when I was student, teacher said always they said something like this, but I'm very unhappy about that. I can understand why these guys always satisfy this relation. And this is why I'm talking about the vector space before this lecture. Okay. Yeah, mathematically it is true. So I didn't prove it, but I asked to the student, please remember this idea. Once you offset this assumption, this is not assumption, this is true. You can write down the total wave function by the linear combination of the J. The important thing here is we assume we know J already, right? So the unknown is the coefficient and the energy. And what you have to do is finding this energy and the coefficient. Once we know the coefficient, then we can obtain the wave function because we already know this one. Okay. So the Hamiltonian here, I said 1, 3 and any kind of interaction at the first time we include, but just to think about that, interaction between the number 1 atom and number 2 must be exist. Otherwise, it's an isolated system. But how about the interaction between 1 and 3 and 1 and 4 and so on? Those interaction must be getting weaker and weaker, right? So let's assume the nearest hopping means let's consider only the nearest interaction. So if ij are different, only number 1, then let's say this is beta. This inner product is general. This makes some scalar number, so let's say this is alpha. And if I and j are same, let's say this is alpha. And if I is different from j, more than 1, we ignore the interaction. So let's say 0. So this by simple assumption, if we take the inner product in the right-hand side, then you can write in this one. And this one is nothing else but this guys is, and this is this one. So from here, if taking out the coefficient outside, then we obtained final result is here because we taking the inner product in both sides. This part is here and this part is here because they are linear combination of wave function. We know ij generate they are orthogonal already. Yeah, orthogonal. So in the right hand side, the remaining is only I term. Okay. So if we write this one, what we obtained is such kind of matrix form. The size of matrix is a number of atom n. So n by n matrix, and we can write down this one in this form. So now what we have to do is finding the condition of the non-trivial solution of this coefficient. Means what we need is to find the determinant of this matrix must be 0. Okay, it's the same idea. So now we are talking about the one-dimensional chain here. And how about the end atom here and these guys? The easiest way making the link to connect this one to this one. So let's making this kind of link. So means so C0 must be same to Cn, and Cj is must be same to the Cn plus j, means the periodic condition, periodic boundary condition. So it is necessary to ignore the surface effect. But in real material, the number of n is number of Avogadro, right? It's really, really huge. So in that case, the endpoint effect is not important. So the easiest way is finding such kind of periodic boundary condition instead of the infinite one. Okay. So this matrix is turned to these equations, and finding the trial solution is Cj is kind of exponential phase term. And if you insert this one to here, we obtain the theta, the corresponding phase term can be expressed by this way. And now we have a coefficient as this exponential term. And this is actually same to the Bloch theorem in a solid state physics. Same physical meaning. So now what we obtained is the energy is alpha plus 2 beta and cosine something, cosine phase term. Okay. And this means if you taking the n is a really, really large number, then the theta is kind of a continuous variable, right? The m is an integer number, but the theta, the m is here, varying from 0 to m minus 1. So this number is changing from the 0 to 2 pi. Okay. So this energy, if you're taking this theta, is continuous, nothing else but this shape. Okay. And the bottom of this energy is alpha plus 2 beta, and the top is alpha minus 2 beta. Please remember that beta is negative. And let's think about the finite number. Only one single atomic system, we have an energy of alpha. And we solve the two case, we have a alpha plus beta, alpha minus beta, right? If we have 3 atoms, we have a 3 state and 4 state for the 4 atoms and so on. So, and in infinite case, we have a continuous spectrum of the width of 4 beta, because the bottom is plus 2 beta, top is minus 2 beta. This is 4 beta. Okay. And this shape, this is actually inverse cosine, is the very basic form of the band structure. Okay. So for the n is 5 case, let's assume the total energy, all wave function has the same phase, and they form the all constituent instructions. Then we have a such kind of wave function. The energy of the system is given by this number. And if we have a such shape means the wave function of this part and this part has a opposite sign, and we have this energy, and you can see all destructive case, we have this energy. And now the beta is also negative. This is the large energy, this is small energy. So this is the smallest the ground state of the system, and this is the highest system of the energy. So there's more node, then there's number 1, 2, is 2, this is 3 node, then less stable, right? So just remember that bonding, anti-bonding case in the hydrogen atoms. Yeah, once we have a node, it means it's high energy, means less stable. So from the atom to the solid, this is the distance between the interaction. In this large distance, every atom has their own energy. But when they start to interact, this is the s electron and the p electron energies. They start to form the band, and this is the real distance of the atoms. Then we make such kind of band gap, or depends on the distance of atoms. And the distance of atoms depends on this band gap, and this band gap determined the basic property of the materials, let's say insulator and conductor and the semiconductor, right? So in a band structure, this distance is the lattice constant is very, very important. They will gonna determine the bandwidth. Why? Because this distance will determine the beta. This is means the Hoping integral of the two electrons to neighboring atoms. So in generally, if the alpha, the distance between two atoms is getting close, usually the magnitude of beta is increased. More easily, electron can be moved, right? So the band gap is increased because the band gap is related to the beta, because I said this is 4 beta. So now we are talking about here, and we ignore the second or third hopping. But if you including this second and third hopping, it's not easy, but we can somehow find these terms, additional terms. And look at this. This is the 2 theta or 3 theta instead of the 1 theta. So if we have a 2 theta form, for the single, for this one, we have this shape of the band. But if we have this form, we have a more wavy shape. So we have such kind of band. So if you take a look at the band, if you have such a structure, you can say, okay, there is non-negligible second order hoppings, and so on. Okay. So please keep in mind that point, and let's extend this idea to 2 or 3-dimensional cases. Yeah, their basic idea is same to the 1D case, but we can extend this idea 2 and 3-dimensional, and we can form the Bloch theorems. And the C is depends on the position, and they form such exponential terms. And now we introduce K instead of the theta. Actually, the same meaning. So the wave function has this form, the Bloch functions. And now, for the 3-dimensional case, let's about the simple cubic lattice. The energy of the simple cubic lattice is represented by, okay, this guy is the 1-dimensional chain, right? But this is same for the y and z axis. So we have this kind of energy structure. And this K vector, as you know, this is the momentum space or reciprocal vector space. And actually, this is the Fourier transform of the real space. And the Brillouin zone means the range of the proper K vectors in a band structure. So anyway, I don't know go too depths too deep in a band theory. It's just the introduction. So just to think about the two-dimensional case, let's ignore the third dimension. And this is the energy in a kx, ky state. And the cross-section of this one is inverse cosine, as the same to the previous one-dimensional case. And we can find such kind of a band structure for the two-dimensional case. And the Brillouin zone of this problem is k x, ky is limited by plus minus pi over a. Here a is the lattice constant. And this is the band structure of the free electron. And actually this band is something like parabolic shape of the function of k. So actually this guy has a extended band structure, but if we cut it by the Brillouin zone, we have this guy is going to here, this guy going to here, we have this shape, and so on. So yeah, the energy is here. And this is the Brillouin zone shape for the simple cubic and face center cubic, hexagonal body center cubic. And I hope you guys, you don't know everything of this one, but you have a chance to take a look such kind of a shape for the crystal structure. Okay, so this is the Predator model, and this one is the somehow a real calculation of the germanium band. And look at this left side and right hand side. This part is quite similar, right? Not that big difference, but only difference is there is a band gap here. And this guy is something like this. And if you extend this one, you can easily imagine this guy is actually this one, and this one is something like this. And you can find one-to-one match. So even though the very simple free electron case, still they explain many things of the band structure of the real material. But once we including the interaction, now we have some the gap opening. Without interaction, there is no reason that there is a gap opening. Okay. So now look at this. This is the kind of cosine, the inverse cosine. We said the energy is something like this. So this is you can estimate the beta value of this band from this bandwidth. And how about this? How about this? Every band looks like some combination of the cosine something. Okay? Because the parabolic, the free electron parabolic is k square, and cosine k is when you take the approximation, we have always this form, right? So it should be very similar form. So actually, I showed this the map of the theater once in previous class, and the very important thing of the band is the definition of the density of state. Means density of state is number of state per unit energy at given energy. It's very difficult definition, but somehow means the S here, the total number of state up to energy E means if you talk about the number of seat, the number of seat is actually number of state. So the S is, let's say, S is the function of energy. And what is the S E? Here is the number of seat below this energy. And if you take the derivative, this quantity is density of state. So the density of state at the E is the number of possible seats. Let's say how many seats here. You can count it, right? That's the density of state. So density of state, this energy is small, but this energy is large, right? So if you write down the density of state, the energy, if you have such kind of a diagram, means in this energy there is a large number of seats. Okay, so that's the definition of the density of state. So if you take in the density of state, it's the derivative of the number of energy, and you can write down this way. So the ds is the density of state multiplied by this ring area. I mean this one. This is this ring is the you can say okay. So this is the, let's say this is the mass of this blue ring area, means the volume V. Then it should be volume multiplied by the density of the material, right? So this density of state, physical meaning is same to the density of the material, and this volume, let's say this dV. Volume is the k-space volume. So in this case, the ring area of this ring. So if you take in the total integral, you can obtain the number of state. That's what we need to calculate the many physical quantity. So the blue ring area is what you can calculate is ds multiply this direction, dk perpendicular. And somehow we have a such relation. Density of state is given by the total energy, the ds divided by the gradient of the energy and taking the volume integral. Okay, so this details of the mathematics is not important, but you have to understand the physical meaning of the density of state. Okay, so we have this kind of band structure now. This is an ion, and ion has a very important ferromagnetic material. And let's focus on this band. This guy is, as I said, now you can see this is so this shape is a part of the cosine, right? And how about this? And how about this? All band can be represented by cosine something. This idea is called the tight binding theory. Okay. Anyway, so in this case, what we want to obtain is density of state of the ion. With this band structure, usually paper or the textbook, they give us some those, which one is corresponding. This is energy, and the y-axis is the density of state. So if you take in the integral, we obtain this form. So means the electron can exist in this energy with very high density. And here, there's no the electrons because of very low density of state. And this part is not really band, but the number of electrons is very small. Okay? And this one is total dense stable state. This one is for the S band and for the B band, and this is two type of D band. D band can be categorized by these two. That's the usual notation. Anyway, so the dense stable state of this ion near the most case, the dense stable state near from the Fermi level is very important. So you can say the D band just below the Fermi level is very high because of this guy. And this dense stable state is very important in ferromagnetism. Okay. So let's take a look this band again, this part here. This guy is the bandwidth. Actually, the bandwidth is related to the beta is relatively large. So usually large beta means they are easily hopping. They are moving around. So dense stable state usually small. And this kind of band we call the SP band, and they behave like free electrons and parabolic band structure. So now this two band is corresponding, actually this guy also, corresponding SP character. So they are very itinerant and they are moving around in all metals because of the large beta. But especially in D band, they usually very small beta means the hopping is small means the electron is localized. Okay. And usually they have a large dense stable state because they are existing in a very narrow level of the energy. So if beta is small and the band is small, density is usually large, and they have a localized character. So in many ferromagnetic material, the dense stable state has this kind of shape. This is dense stable state, this is energy. S band usually has this shape. So dense stable state of S band is usually small number. But in a D band, usually they are localized. So the dense stable state at the Fermi level is usually large. This is the typical character of the D band. This is the typical character of the S band or P band. And the Fermi surface is very important concept in a solid state physics. As you know, the electron occupy from the lowest energy state, and it's very similar to the sitting in a theater. They prefer the best view or the nearest side from the stage. Anyway, so if the number of electron is less than total possible seat, means the number of audience is smaller than number of seat, then we can make some kind of boundaries. That's what we call the Fermi energy. The energy of the highest occupied energy state means if you have a such a theater and only audience occupied seat here, this is the what we call the Fermi surface. That is very important to why an electron below the Fermi level, to interact this electron with the outside, you need a certain amount of energy. For example, this is the Fermi level, electron is here, and if we have a very small energy, let's say, okay, let's think about the red light photon, then they can interact only the electron below to the two electrons. And if we have a smaller energy electron, they can interact only the surface of the Fermi level. For example, conductivity case, if you apply the electric field, let's say this electric field, only the electron at the Fermi level can be moved. Okay, so they are it's like the valence electron for the chemical bonding. If you have many electrons in your molecule, but only chemical bonding or chemical reaction occurred at the highest energy electrons. So that's the meaning of this Fermi energy here. Okay, and so the property of the electron at the Fermi level is very important, and the shape of this Fermi level, called the Fermi surface, is nothing else but the equi-energy surface in K space, and the shape of this Fermi surface is very important in many physical quantities. Okay, so let's back to the real shape of the Fermi surface. Just recall the inverse cosine shape here, and this is two-dimensional version of this idea. And let's think about the small filling case, means the number of electrons is very small. So only the bottom of the band is occupied. So in the case, we think about the small k value. So we can take the approximation, and this is the cosine kxa is this approximation, and we have this form. And the Fermi level can be expressed by this way. And in a K space, this is nothing else but the sphere, the circle. So we have this kind of circle shape, and you can obtain this value called the Kf Fermi surface, Fermi wave vector, and something actually not this one, maybe here. And if we have a half filling somewhere here, this term is almost zero. So we have such a square shape of the Fermi level, Fermi surface, or little bit bent to square shape. And this is some real Fermi surface, the kappa. And now you can understand what's going on here. This kind of shape came from here. And almost full filling case, electron is something here. We can take another approximation, and Fermi level has such kind of part of the circles. Okay, so this is the real Fermi surface of the copper and natrium and other materials. This is a periodic table. And if you take a look at this link, you can find the Fermi level, Fermi surface of any single element materials. And it looks very, very complicated, but look at this. These guys looks quite similar. This guy is also similar, and this guy is very similar, and similar. These guys looks quite different, but if you take it by each band, I mean the D band, S band, P band, then you can find there are similarity also. Anyway, so that's why the period table has a similar property along this line. Okay. And I think I should finish that. Okay, I think finished here, and let's keep going. Next part in Wednesday. Okay, so thanks. We'll see you Wednesday.